Up to this point in Unit 5, we have learned the basic relationship between a function and its inverse. Then, in Section 5.2, we learned about the first half of an inverse pair, that is, an exponential function. In Section 5.3, we're going to learn about the second half of this inverse pair, logarithmic functions. Section 5.3.1, Definition of Logarithmic Functions. Definition: x equals a to the y is equivalent to y equals log base a of x for a greater than 0, a not equal to 1, and x greater than 0. We have to have a very basic understanding of logarithmic functions so that we'll understand how to solve the equations in the next section. So let's begin with this statement right here. X equals a to the y. Do you notice anything different about it? Does it bother you for any reason? Does it catch your attention? How does it contrast with what we learned in Section 5.2? Well, in 5.2, we learned about the exponential function y equals a to the x. Did you notice that x and y have been switched? Now, what happens when we switch x and y? Well, when we switch x and y, symbolically we're reversing the domain and the range, and we're creating an inverse function. So these two functions are inverse functions. X and y have been switched. So when we look at x equals a to the y, we are dealing with the inverse function of our basic exponential function. Now, in the expression or the equation, x equals a to the y, it is not in function notation. Generally, in function notation, we have y isolated, and it's equal to some sort of operation applied to x. So what we're going to do is isolate that exponent. At this point, we don't have the tools to do that, and so now we're going to learn about logarithmic notation. Logarithmic notation is simply a rearrangement of this inverse function, x equals a to the y. So, x equals a to the y is equivalent to y equals log base a of x. So you can think of that logarithm as simply a rearrangement of this exponential function, which represents the inverse of our basic exponential function. Notice y is isolated, and it's equal to an operation applied to x. So let's look at the anatomy of this logarithmic expression. Now, log, L-O-G, log, that is short for logarithm. This is the function name. It's sort of like the f in f of x, right? So when we say log log, that's the name of the function. The subscript there, base a, is known as the base of the logarithm. That base a is the same as the base in our exponential equation to the left. Notice the restrictions on a has to be greater than 0 and a is not equal to the 1, are the same restrictions that we applied to the base in our exponential function when we defined exponential functions. And then the last part of our logarithmic expression here is the x. X is the argument of the function, or the argument of the logarithm. So it's like the x in f of x. That's what we're plugging into the function. So x equals a to the y, which is a rearrangement of our exponential function, right? We've switched x and y to create the inverse function. Then we're going to rewrite this in logarithmic notation. Thus, the exponential function that we began with, y equals a to the x, is the inverse to y equals log base a of x. The relationship between an exponential function and a logarithmic function is the same as the relationship between addition and subtraction, or the relationship between multiplication and division. The operation that the exponential function achieves is the exact opposite of the operation that the logarithmic function achieves. They are inverses of each other. One reverses the other. Now, to further our understanding of logarithmic functions, now that we're familiar with the notation, we want to practice converting between forms. We want to go from logarithmic notation to exponential notation and vice versa. So the fundamental key in understanding how to do this is found in this definition right here. X equals a to the y is equivalent to y equals log base a of x. So in example 1, we're going to use this relationship to convert each exponential equation to an equivalent logarithmic equation. This is a very simple skill, and this is going to be one of the methods that we're going to use to solve equations later on. So starting with the exponential equation, 2 to the 4th equals 16. We're going to rewrite this as a logarithmic equation. So we're going to identify that we're going to a logarithm by identifying the function name log. The base of the logarithm is the same as the base of the exponential equation. So here our base is 2. We're going to write that as a subscript on our logarithm. Now, the argument of the logarithm, x, notice that's the result of raising that base to a power. So the argument is over here on the other side of the equal sign. Now, log is equal to y, and where did y come from? Y was the exponent. So log base 2 of 16 is equal to 4. At this point, you can observe the logarithm, log base 2 of 16, is equivalent to the exponent 4. So a logarithm represents an exponent. That'll be an important fundamental result for your understanding of logarithms. Now, let's try that pattern again. Example B, 2 to the negative 4th equals 1/16. So I'm going to convert to logarithmic form. The base of the exponential equation becomes the base of my logarithm. The argument is the result of the evaluation. So I'm going to put 1/16 in the argument, and this is equal to the exponent. The exponent is always isolated for the logarithm. Getting used to that pattern is going to help your understanding of logarithms. Let's try the next one. The base of the logarithm is the base of the exponential equation. So in this case, it's 1/3. The argument of the logarithm is the result of the exponential evaluation, and the logarithm is equal to the exponent, -2. Now make sure you watch your levels, write it carefully. You want to make sure that your logarithm, your argument, your evaluation are all on the same line, and the base of your logarithm is a subscript. I've seen students get a little bit confused with their levels, and then they're not sure what the logarithm actually means. So the way you write it does affect the way you understand it. So make sure that you write it carefully, just like a teacher to tell you to write neatly, right? All right, let's try a to the b equals c. The base of the logarithm is the base of the exponential equation. The argument of the logarithm is the result of the evaluation, and the exponent is what's isolated in the logarithm. So this is the base. This is the result of raising a to the b power. Whoops, get my c back in there. If you want to pause the video and try the next two check boxes and then turn it back on, let's see if you get it right. 2 to the negative 5 equals 1/32 could be written log base 2 of 1/32 equals -5. Again, check your baseline. Make sure that you've written everything in the correct position. And then finally, log base y of 1 equals 0. Hope you got those right. So that is how we go from exponential form to logarithmic form. Now we're going to reverse that process. This time we're going to start with a logarithmic expression and convert to an exponential equation. So the first thing we want to do is identify the base of the logarithm. And a lot of times you can see this is just making a circular pattern here. We're going to take base 4. The exponent is over there on the other side of the equal sign, and this is equal to the argument of the logarithm. Now, looking at 4 squared equals 16. because it's familiar, we understand that that is definitely a true equation. What you want to understand is that this is stating the exact same information as what we have over here. So again, we are looking at going from logarithmic form to an equivalent exponential form, which represents the opposite of where we have been. Let's try that again. Log base 25 of 5 equals 1/2. So the base of the logarithm becomes the base of the exponential equation. We're going to come over here to the other side of the equals to get the exponent, and it's going to equal the argument 5. Now remember, when we have a 1/2 power or a rational exponent, we can rewrite it in radical form. So the base of the fraction becomes the index of the radical, and our 25 becomes the radicand, and the numerator is the outside exponent. So essentially what we have written here is the square root of 25 equals 5. It's just written with a rational exponent. Looking at our next example, we're going to take base 11. We're going to pick up the exponent over here on the other side of the equals and set that equal to the argument. Observe, 11 to the 0th power is equal to 1, and that means exactly the same thing as the rearrangement log base 11 of 1 equals 0. The next example, the base is 2. The exponent is over here, -3, and this gives us 1/8. Now think about what we learned about negative exponents. If I were to evaluate 2 to the -3, remember we would move that to the opposite place in the fraction and then change the sign of the exponent. 1/2 cubed is the same thing as 1/8, so we have written it correctly. The next example, we have base 3, exponent 1 equals 3. And then finally, base 2, exponent x equals 6. So in those two examples, we've been converting between logarithmic form and exponential form. One thing to observe is that when we look at the logarithm on the left side, it's equal to the exponent. So in the next example, we are going to evaluate logarithms. That means we're going to be finding an exponent. When you work through these problems, you can kind of talk to yourself, and you can ask yourself a question that will focus your attention on what it is you're trying to do. Ask yourself, base to what power equals the argument? Base to what power equals the argument? So on example 3, evaluate the following logarithms exactly. I need to figure out 3 raised to what power is equal to 81. So I'm going to think of this problem when I evaluate the logarithm. 3 to what power equals 81. Now, if you're unfamiliar with the powers, you can certainly experiment with that with your calculator. You can just try out several powers of 3. 3 squared, I'm sure you're familiar, that one is 9. 3 to the 3rd power is 27. 3 to the 4th power, that's the one that gives us 81. So we know 3 to the 4th power equals 81. Okay, thus the original logarithm that we were trying to evaluate, we can say thus log base 3 of 81 equals 4. Okay, so this part was just the means by which I used to find the answer. The answer here is 4. So when we evaluate a logarithm, we're trying to figure out what power can I raise this base to. Notice the base is a subscript. It's lower, right? I need to raise it to a power. 3 to what power is going to achieve the result 81? On the next one, we can follow that same process. Log base 3 of 1/3 equals something. We're trying to find that something. Here's how we're going to think about it. We're going to say base 3 to what power equals the argument 1/3. Well, notice I've got a 3 on the left and a 3 on the right. The 3 on the right happens to be in the denominator. The 3 in the denominator over there has an unwritten exponent of 1. To get 3 out of the numerator into the denominator, we know that we can achieve that with a negative exponent. Thus, I have found the appropriate exponent. Now, remember, we can say therefore, or thus, the 3 little dots mean therefore, log base 3 of 1/3, our original problem, has a value of -1. Okay, let's keep practicing. Now, the better you understand the logarithms in this section, the easier it will be when we start solving equations. So log base 3 of 1 equals some value. So I'm going to think of this to solve the problem. 3 to what power equals 1? So when I evaluate a logarithm, I'm looking for an exponent, right? Bottom line, a logarithm represents an exponent. Well, the only way I can get a 1 out of that is if I raise 3 to the 0th power. Thus, we can say, therefore, log base 3 of 1 equals exponent 0. Now, as I've been writing these problems, maybe you have formulated the question, when are parentheses necessary for the argument? When are they not necessary? Well, if you look on example A, the way this one is written, the argument is not in parentheses, and the way that I wrote it here, the argument is in parentheses. Either way is correct. You will see me always set the argument off in a set of parentheses, just to indicate it is an argument and it is not part of the function name log, but you can write it without the parentheses. Okay, next question. Log base 6 of square root of 6. We're trying to figure out what that is equal to. The way we're thinking about it is base 6 raised to what power equals the square root of 6. Well, as we mentioned previously, the square root can be represented by the 1/2 exponent. So therefore, log base 6 of the square root of 6 is 1/2. So I'm just recognizing that the exponent here on the 6 is 1/2. And remember, to evaluate a logarithm, we're looking for an exponent. If you want to pause the video and work the next 2 check problems, turn it back on, you can check your work. To evaluate log base 2 of 32, I'm going to think of this as 2 to what power equals 32. Now, if you don't sit around evaluating powers all day and you're unfamiliar, remember you can make use of your calculator to sort of detect that problem. 2 to the 5th is equal to 32. And by the way, the more you practice, the more familiar these numbers will become. And you'll probably be able to evaluate them without a calculator. So log base 2 of 32 is equal to 5, because the exponent that I'm looking for there is 5. Now, the last one, notice, is just like example D. So the base has changed, but the exponent represented there is the same. So log base 2 of the square root of 2 is 1/2.